today's lesson we're dealing in how to design a gear. And with the gear bending stress, we're tackling with the Lewis equation. So we have the bending stress, the velocity factor, the power transmitted, the KO, the KM, the F, the M, the J, which all these parameters are listed over here. So we'll be given a question to solve, and we appreciate how to solve this given equation using the given parameters. We have to calculate the bending stress. We first list our parameters. So we know that the speed was given to be 1250 revolutions per minute. The power transmitted is 5 kilowatts. The module is 4 millimeters. Always know that the module is always measured in millimeters. The angle was given to be 20 degrees, with the driver having the number of teeth to be 20 teeth. Are you getting it? So to solve for the Lewis bending stress, we then write our formula down. KV WT KO, the mounting factor, divided by the phase width, the module, and the geometric factor. So let's first solve the transmitted load. So we have free space, okay? So then WT, its formula is given by 60,000 times the power transmitted divided by pi dn. And we don't know the d, it wasn't given in the question. But I know that from the parameters of gears, the module is given to be d over the number of teeth. So then to get the d, now we have m, we have n. You can now solve for the d. So then to do this, we then make d the subject in this equation. So the d is equal to n times m. So we come here, WT, that's a transmitted power or transmitted load, is 60,000 times the 5. Always make the power to be in kilowatts. So then 5 kilowatts, all divided by the pi. What's the d? What's the n? 20. What's the m? 4. So that's for the d, and the n, that's the speed, is 1250 revolutions per minute. So when we have this, the WT to equal, we have 0.9549 kilonewtons. So we are done with this part. Let me use the red ink. So we're now solving for the factors. So let's go first with the velocity factor. No, it's a factor. Always know that with factors there are no units. So the kV, because it's produced by milling, when we read from the chart, you can see that it's 6.1 plus V all divided by 6.1. This is for cut or milled profile. So then we know that velocity, its formula is given by pi. In designing, there are formulas, okay? You don't have to stress yourself. Over 1,000 divided by 1,000. We know the d, we know the n. But here with the velocity, the n must be in revolutions per second. But in the question, we're given in revolutions per minute. So then v is equal to dn divided by 60 times 1,000. So then in writing this, we have the v to be the pi times, what's the d? The number of teeth times the module times the speed, all divided by the 60,000. So we then have the V. When you punch this on our calculators, we have the velocity to be 5.236 meters per second. But that's not what we are finding for. We are looking for this to find for the kV. So then we put this into the equation, plus 5.236 all divided by 6.1. So the kV, punch on our calculators, we have it to be 1.858. What unit will we write over here? There is no unit because what? It is a factor. So we note this one down. So we'll be finding for the KO. We know that from the question, the uniform input speed was given with moderate shock, and from the table for the KO, we can see the uniform for the driver and the moderate shock for the driven machinery. So when we map these two parts, we have the KO to be 1.25. So we write for a uniform source power, with what? Moderate shock. The KO is equal to 1.25. So all this forms parts of the designing process. Okay, so let's come to the mounting factor. So write our Km. So because we are told to use the minimum particle phase width, we know that to use this from our gear parameters, we must fall within this range, 5p. And p here is equal to pi m. So 3 times pi m, that's 4, is equal to 4 pi. And all this is in what? Millimeters. One just on our calculators, you have the phase width to be 37.699 millimeters. Are you getting it? So then this is between the range of 0 to 2 inches. So when we bring this into inches, it's less than 2 inches. Are you getting it? So then we write our statement. Assume for accurate, because no information was given, the Km is equal to 1.3. So this is our Km, this is our KO. So it's now left with the geometric factor. The geometric factor, that's the J. So for the 20 degrees full depth, when we pick the table, we see the driver and the driven. So now, with the table, with 20 being the number of teeth for the driver, with the number of teeth for the driver is here, and the driven is here. So now 20 here is the number of teeth for the driver, and the driven was 50. So once we map this down to 20, we can read 0.34. Are you getting it? It's close to the 0.35. Are you getting it? So let's continue with it. So with this part, we are done with finding the parameters. So we write our equation back again. The F, the M, the J. We've been able to solve for the kV. So I'm just writing the values we had, okay? Times what? 0.954 49. We had the phase rate to be what? Because it was minimum. What do we get? 37.69 times the module 4 and the factor, geometric factor. Let's know that this was in kilonewtons, so then times 10 raised to the power 3. This was in millimeters, and this also was in millimeters, so then times 10 raised to the power -3 times 10 raised to the power -3. Are you getting it? Bringing everything to their normal unit. When you punch this on our calculators, we have 5623260.8 Pascal. But we must bring it in what? Megapascal. So then have this to be 56.23 megapascal. So this is the bending stress for the gear using the Lewis equation.